On this worksheet, we're going to practice evaluating or assessing the quality of resonance structures, like trying to decide if some resonance structures are better than others. And the first problem on here has us just coming up with a list of 3 characteristics of bad structures, but I'm actually going to save this for last, because what we're going to do is draw some resonance structures down here, and then just sort of use our intuition to classify them as either good structures or bad structures. And once we've done that process, then we'll go back up here and kind of generalize what makes these structures bad. So for these 3 molecules, we are going to draw 2 resonance structures for each one of them. With resonance structures, remember, you are not allowed to change the connectivity of the atoms. That means the connectivity refers to the way the atoms are actually connected to each other. So I'm starting out just by redrawing the connectivity of the molecule. I'm connecting everything with single bonds because, that's what holds the atoms together. That's a good starting point. And I'm going to make 2 of these because we want to draw 2 structures. Another thing that I'm going to do, I don't know why on this particular problem I didn't include the lone pairs on the oxygen, so I'll put those in. So when we're coming up with our own resonance structures, meaning that, we have to figure out what this looks like and figure out what this looks like, we're going to start by looking at the original molecule, and we're just going to ask ourselves, what can we do to that molecule in terms of resonance? Now, when we're working with resonance, when we're coming up with resonance structures, we only have the option of taking a lone pair and turning that into something, or taking a double bond or a triple bond and turning that into something else. So when we're looking at this molecule, the only options that we have for that one particular molecule is messing with either one of our lone pairs or the double bond. All the rest of the bonds in the molecule are single bonds, and those are things that we cannot touch. Now, lone pairs in a molecule, if we're going to do some resonance with them, all that we can do with a lone pair is turn it into a bond. And when we choose to turn a lone pair into a bond, we have to form that bond in such a way that the electrons stay associated with the same atom. So for example, if we wanted to take these electrons right here and turn them into a bond, we would need that bond to be connected to the carbon atom that the lone pairs were originally associated with. If we have a double bond or a triple bond, most of the time we're going to be turning those into a lone pair, but we could, I'm going to write this a little bit better, most of the time we're going to turn them into a lone pair, but we could use them to make another double bond or another triple bond. That's not as common, but it is possible. So with this structure right here, we've got a lot of choices of what we can start with. I think that I am going to choose to start with the double bond between the carbon and the oxygen atom, and I am just going to take those electrons, so the electrons that are in the double bond, and I'm going to move those electrons onto an atom. I could move them onto the oxygen atom, or I could move them onto the carbon atom. The electrons in the double bond just have to stay associated with one of those 2 atoms, and I am going to just choose to move them up. Now, you might be wondering right now, how am I making that decision? How do I know that that's what I'm supposed to do? And I want to clarify that I don't know what I'm supposed to do. Could be doing anything right here, as long as I'm following these rules. So I don't have to start with that. I could have started with the other lone pair instead and moved those electrons in. There's a few different things that we could have done. You just sort of have to make a decision of where you're going to start and go with that. So let's say that that's what I choose to do, and with that curved arrow, I'm going to complete the second resonance structure. So since I didn't do anything to the carbon on the left, its formal charge is staying exactly the same. The carbon in the center, carbon number 2, its double bond has turned into a single bond, and I have now added another pair of electrons onto the oxygen atom. Whenever you change the bonding for any atoms, you should always recalculate their formal charge, because chances are good that the formal charge has probably changed. So for the carbon number 2, its formal charge is now +1. And for the oxygen atom, its formal charge is now a -1. And we need to come up with one more resonance structure. So what could we do with that? Well, again, we can only work on lone pairs, and it doesn't make a ton of sense to take one of these lone pairs and put it back. That's just going to recreate this structure here. So what I'm going to do is choose the other lone pair, the one on the carbon, and I am going to move that in to make a carbon-carbon double bond. That's going to be right there. I'm still going to have those 3 lone pairs of electrons on that oxygen and the negative charge on the oxygen because I didn't do anything to the oxygen. But since I did change things for these 2 carbons, I need to recalculate their formal charges. This carbon atom is a formal charge of 0, and this carbon atom the same. So no formal charges on those. So let's actually, before we do any classification, let's just practice drawing all of our resonance structures first, and then we'll go back and do some classifying. So here is our next molecule, and let's kind of take a look at what we're working with here. We could choose to start with our double bond or any one of the lone pairs. I think for this one, I'm going to choose to start with the double bond, just like I did in the last problem. And I'm going to take that double bond and I'm going to move the electrons onto either one of the carbon atoms. So I could move them here or I could move them here. Totally my choice. I think I'm going to choose to move them this way, like that. And so that is going to give me, remember when we move a bond, the electrons turn into a lone pair. When we move a lone pair, the electrons turn into a bond. So since I changed things for those 2 carbon atoms, that means I want to reevaluate the formal charges on these atoms. This carbon is 4 minus 3 minus 2. That is a formal charge of -1. And the other carbon atom, 4 minus 3 minus 0, is a +1. So now what else could I do? Again, all I have, are a bunch of lone pairs. I don't want to move this lone pair back because that's going to recreate this structure. So my only choice is to take a lone pair from the bromine and move that in to make a double bond in that position. And that structure will look like this. Since I didn't make any changes to the carbon on the very left, I know automatically that that has a negative formal charge. I did make some changes right here, so we need to calculate these guys' formal charges. That carbon is a 0. This bromine, 7 minus 2 minus 4, that's a positive formal charge, like that. And then we have one more set down here. So what can we do with this? This one's kind of easy to start with because we just have this lone pair of electrons on the sulfur. These are our only choices to start. When we turn these electrons into a bond, the bond needs to be still associated with the sulfur, so either the left side or the right side. And we cannot put the double bond in this position because that would give this carbon atom way too many bonds, 5 bonds. So our only choice with this one is to take a lone pair and put it here in between the sulfur and the carbon to make a sulfur-carbon double bond, which will look like this. And then we want to reevaluate formal charges for these two atoms. The sulfur is 6 minus 3 minus 2. That's going to be a +1. And the carbon has a formal charge of 0. Now we have to think about what else could we do with this. Well, we do have another lone pair. We've already talked about why it can't go this way. The lone pair also could not go this way because that would give this carbon atom 5 bonds. So the only thing that we could do is move one of the sets of electrons in the double bond. We don't want to move them back to the sulfur to recreate this structure. So what we'll do is move them in the other direction onto the carbon. And that will give us a structure that looks like this. And since we've changed the bonding here and we want to reevaluate the formal charges here, this sulfur formal charge is a +2. And the carbon's formal charge is a -1. Okay, so what we're going to do next is look at these structures and decide whether they're good or bad. So we're going to kind of evaluate them. And the easiest thing to do is to find the bad structure. Of these three, what we're going to do is pick the one that is the absolute worst. And we're just going to try to use our intuition. When we look at all three of these structures, we're looking for something about one of them that makes it look worse than the others. And the one that I'm picking is this one right here in the middle, and hopefully you picked that as well. Again, we're just sort of using your intuition. We're picking this structure. The reason that hopefully you focused on this structure is because of the number of formal charges that it has. Remember, a formal charge represents an unhappy atom, an atom that's got something wrong with it. This and this resonance structure, they each only have one formal charge, whereas this one has got a ton of them. It's got 3 unhappy atoms. And so we have to ask ourselves, why would a molecule with 1 unhappy atom convert itself into a molecule that has 3 unhappy atoms? This conversion makes sense. 1 unhappy atom, another unhappy atom, 1 each, that's fine. But this isn't any good at all. Let's go down to this one and let's see if we can figure out what's bad about this set of resonance structures. In fact, there's a lot of bad resonance structures here. I don't like this one, and I also don't like this one. You may have, I feel like this one's probably harder for students to pick. You may have picked this to be the worst resonance structure because of the positive charge on the bromine. Typically, electronegative atoms like bromine, they like to be negatively charged. A lot of times when we think about halogens, we think about them in their anionic form, like bromide or chloride. We don't often think about bromine having a positive charge. That's kind of a weird situation. Another thing that I don't like about these structures is that they have a lot of formal charges. Like this one has none, but this has 2, and this also has 2, and that's not great. One thing that you may have not picked out about this structure is that it has a formal charges that are side by side. I'm going to call this a bad structure. So we have 2 atoms that are bonded together that have opposing formal charges, a negative charge on one and a positive charge on the other. That's not the same as what we have over here because these 2 atoms are not bonded directly to each other. But here we've got these 2 atoms that have opposing formal charges bonded directly together, and we have to ask ourselves, why would they do that? Why would we have one atom that's electron rich and unhappy about it, and another atom that's electron deficient and unhappy about it? Why wouldn't the electron rich atom just move its electrons over so that everyone is happy? This isn't a great situation either. And then last but not least, what do we have down here? Looking at these ones, I feel like this one's easier for students to pick out. The bad structure right here, here it is. This is the worst structure, because you're probably recognizing that 2+ on the sulfur, that's a really high charge. It's also a positive charge on an electronegative atom. Also, the sulfur is electron deficient. It doesn't have its octet. It only has 6 electrons around it. So there's a lot of bad things going on for this molecule right here. And if we even want to go a little bit further and compare these 2 structures, this, not great. If I have a positive charge in a molecule, I don't want to place it on an electronegative atom. I'm okay with putting a positive charge on a carbon, but not on an electronegative atom. So after observing these things, let's just kind of make a list of what we didn't like about our bad resonance structures. One thing that we saw that was sort of like a red flag was a lot of atoms. So we saw 3 atoms. But we could also maybe see more, 3 or more atoms with formal charges. It doesn't even really matter what the formal charges are. Like once we start racking up a lot of formal charges in a molecule, we decide that that's not a great configuration for that molecule. And why would it want to have so many atoms that were unhappy? Another thing that we saw, let's take a look down here at this one, putting positive formal charges on elements that are known to be electronegative. I didn't even notice until just now that this bromine is also only having 6 electrons, so it doesn't have its octet. And that's a bad thing. So positive formal charges on electronegative atoms, not good. Negative formal charges on electronegative atoms is generally fine, because electronegative atoms can handle having a little bit of extra electrons on them. That's what it means to be electronegative. But a positive formal charge on an electronegative atom, something that does not make us happy. Having a high, or we would also feel this way if it was very negative, so a big formal charge is also a bad thing. I'll add this to the formal charge list. So, I mean, how would I describe that? Formal charge of 2 plus or 2 minus or more. Either larger or smaller than that. That's bad. And then the last thing that I talked about that is not quite as intuitive is having the atoms that are bonded directly to each other with opposing charges. Because I talked about, why would they distribute their electrons unevenly in a way that makes two atoms unhappy? So having adjacent atoms that have opposing formal charges, that just doesn't make a ton of sense. It's okay if they're not directly connected to each other, not good if they are directly connected to each other. So we'll describe that as two atoms that are bonded together with negative and positive formal charges. Now, there is one exception to this rule, and as far as I know, there's only one exception, and that is a little sort of functional group called the nitro group, a little group of atoms called the nitro group. The nitro group, in its happiest configuration, has an oxygen with a negative charge and a nitrogen with a positive charge, and this is the best case scenario for nitro. But like I said, as far as I know, that is the only exception. So these are things that you want to avoid when you're drawing resonance structures. If a resonance structure has any of these characteristics, it just is so bad, there isn't really any point in even drawing it. So looking at these structures that we drew, if we were being asked to draw resonance structures for this molecule, there would be no reason to even bother drawing that structure because it's really, really bad. There would also be no reason to draw this structure. And actually, if I'm being perfectly honest, there really isn't any reason to draw that structure either. Like, there just isn't any good resonance structures for that molecule at all. And with this one down here, no reason to draw that structure just because it's so bad. So knowing what makes a resonance structure bad, you can avoid wasting your time drawing any of those when you're being asked to draw a set.